There you go. Hello everyone, we're Squirrel, and today we're going to be going over our final presentation. First, before we get started, I'd like to introduce everybody. I'm Zachary Register, I'm the Chief Engineer for our group and a geometry member.
I'm Daniel Chatula, member of Stability and Control and Trajectory and Performance.
My name is Omar Velasquez. I'm lead of Waste Balance Structures and Materials, also in WBSM, and also a member of Geometry.
I'm Elliot Oliver, lead of propulsion and a member of WBSM.
I'm Creed Carlo, I'm the lead for Geometry and Systems and a member of WBSM.
I'm Stephen Hendrick, lead of cost and market and secondary and trajectory and performance.
I'm Ryan Evans, I'm the Stability Control Lead and Secondary for Aerodynamics.
I'm Mohamed Perez, and I'm a member of Stability and Control and Cost and Market.
I'm Brendan Trussell, I'm a member of Aerodynamics and Propulsion.
I'm Richard Baton, Trajectory and Performance, or TAP lead, and member of Propulsion.
I'm Zachary Reynolds, I'm the lead of Aerodynamics and Aerothermal and a member of Synthesis.
With everyone introduced, now we can introduce the project. The goal of this project is to reverse engineer the Dream Chaser Tenacity, which is the uncrewed variant of the Dream Chaser product line by Sierra Nevada. To do this, we'll develop an iterating project sizing methodology to assess the feasibility of the design, generate a payload weight to orbit and a vehicle slenderness solution space, and perform a technology assessment to assess the feasibility of the vehicle. Let's start with the Dream Chaser concept's origins. The Dream Chaser dates back to the HL-20 designed by NASA in the 1980s, which was a reverse engineering effort on the Russian Bor 4. The HL-20 was intended to serve as a low-cost alternative to the space shuttle. Unfortunately, no prototypes were ever built, but extensive wind tunnel data and design analysis was performed on the vehicle design. In 2005, Sierra Nevada bought the rights to the HL-20 design and updated it with modern materials. It was intended for crewed missions to the ISS like the HL-20, but it did not win any contracts. So in 2015, it was reimagined to perform unmanned cargo missions to the ISS with the addition of a disposable cargo module named the Shooting Star. To perform this reverse engineering project, we chose the ABDS conceptual design process. This process has four main phases: project initiation, where the basic vehicle design families and mission architectures are selected; parametric sizing phase, where the vehicle is then sized and undergoes assessment and screening, finding dead horses and living horses. It then goes into configuration layout, where an outer mold line and a rudimentary internal layout and a more detailed mission profile is generated. In the configuration evaluation, where if time permitting, the solution space is reconverged, a design and risk assessment is performed, and a final baseline vehicle is selected. With the process overview complete, we can now go into the first stage of it, project initiation. As mentioned before, the main objectives of this phase are to identify potential vehicle design families and potential mission architectures. Synthesis is going to primarily be heading the vehicle design family selection aspect of this phase, while trajectory performance will handle most of the mission architecture. To meet its objectives, the synthesis utilized the project briefing and ABS literature in order to make its key decisions. The primary one being, this is going to be a lifting body vehicle. This was stated in the project briefing and it is a requirement for the project. In addition, we identified several key parameters, the big ones being the slenderness ratio and the internal payload weight, which form the foundational trade matrix for the synthesis discipline, and then the takeoff growth rate and planform area, which serve as the domain of the solution space, which becomes very important in the subsequent phases.
While Synthesis identified the selected design family, Trajectory and Performance defines how the vehicle actually flies by establishing the initial mission profile and its key parameters. The key parameters, shown in the table on the right, directly drive what the mission can and cannot do. These inputs come from real systems such as the Vulcan Centaur for the ascent, Space Shuttle, HL-20, and Dream Chaser for orbital and re-entry constraints. With these key parameters, we can construct a physically consistent mission timeline. We launch on a Vulcan Centaur from the Space Launch Complex 41 at Cape Canaveral, insert into an initial parking orbit, perform phasing and rendezvous within a Delta V constraint, and then deorbit. From there, we transition through hypersonic to subsonic flight and perform a controlled glide landing at the shuttle landing facility. This profile serves as a backbone for propulsion, thermal, and control design moving forward.
With the vehicle design family and mission and architecture selected, we can now move into sizing the vehicle in the parametric sizing phase. The main objectives of this phase are to develop a convergence process, generate a solution space, screen that solution space, and then select a sized vehicle. Synthesis takes a primary role in this phase as it provides all of the major deliverables for the phase. However, it's not an island. It requires inputs from WBSM, geometry and systems, propulsion, trajectory and performance, and aerodynamics and aerothermodynamics to properly both generate and screen the solution space. Because this is such an interdisciplinary process, we've created simplified flow diagrams to show how we go from the inputs for this phase through the various disciplinary connections to achieve our outputs and objectives for this phase. For the synthesis-specific aspect of the process, we had to rederive the convergence equations because our vehicle does not have one of the fundamental aspects required by the ABS convergence logic, that being a propulsive system. After rewriting the equations for a glide vehicle, we then had to define what the solution space actually contained and represented. The main decision that we came to is that the solution space would only include the Dream Chaser portion of the vehicle, and that the tow and platform areas would be for the body only, as the wings are considered control surfaces and will be added in subsequent phases.
The objective for the weights and balance team in this phase was to determine important weight budget terms, values for them, and then for this we took various inputs from the other disciplines, as well as some parameters from our literature search. For this, for our weight estimations, we apparently used CASA for its focus on hypersonic vehicles, and then compensated for our expected use of composites in our structures.
We validated this method using the space shuttle and the HL-20. As you can see, all of our percent error values are below 10%, which is what is promised by the CASA method. Once verified, we gave this method to synthesis to incorporate into the weight budget of their convergence logic to produce the solution space. Once a design point is chosen from the solution space, which synthesis will discuss further, a component weight breakdown can be generated for this sized vehicle. These component weights will be important for use in CL.
For geometry, our goal in PS was to deliver the geometry variables that synthesis used for convergence logic. Because of the way that synthesis defined our tau in the beginning, we decided to increase the tau from 0.2 to 0.25. And we did this based on calculations in our literature. For our KW values, we used the blended body KW tau relation equations, and we verified it using this plot and other vehicle data. And then for our volume coefficients, we used the transatmospheric launcher sizing, and we pulled those directly from it.
Propulsion's objective in PS was to calculate the parameter values needed by the other disciplines. Most of the inputs for this came from literature review. Based on the values listed in Sierra Space Hardware Catalog, we calculated these output parameters for the engines that they used on the Dream Chaser. These then went to synthesis for the weight and volume budget equations and TMP for the weight ratio. We then compared these engines to similar RCS engines, and as you can see that how the thrust is quite similar, the engine thrust to weight ratio is much lower. This informed our decision to resize our own engines in CL.
The goal of trajectory and performance during the PS phase is to find the weight ratio of our vehicle. To do this, we use the classic rocket equation with an input from propulsion, and we needed to find the total delta V of our vehicle during the mission. We then use the Holman transfer maneuver to calculate the delta V required to raise our initial insertion altitude given to us from the Vulcan launch vehicle to the ISS's altitude. We then calculated the delta V required to deorbit our vehicle and return home. The total delta V found, we were able to find our weight ratio, and then we needed to verify this method. To do this, we ended up finding other orbital vehicles that delivered payload to the ISS, and so we calculated their weight ratio and compared it to the documented version, found a low percent error verifying our method, and from there we gave our weight ratio to synthesis for their solution space generation.
Now that the trajectory has been defined and a range of geometry values have been established, aerodynamics was created an aerodynamics model. This must be parametric in order to capture the range of vehicle sizes that will comprise the solution space created by synthesis. To begin, for the subsonic regime, we used a mix of hybrid and analytical and empirical equations applied to lifting body geometry specifically. And for the supersonic regime, we used a historical approach based on historical programs like the HL10, FTL7, and M2F2 programs. To model the transonic regime, we used the Fair curve between the two Mach ranges. As you can see here, the finished model, once it was built in MATLAB, is able to output the lift coefficient and drag coefficient of every vehicle in the solution space. When compared to the HL20, the average lift to drag ratio error is about 13% across the mock range. And finally, this model can be delivered to trajectory performance and synthesis so they can use it to screen the solution space.
With all of the disciplinary inputs determined and the screening methods figured out by the various disciplines, synthesis then went and integrated all of these inputs to generate the solution space for the parametric seismic phase. We then integrated the screening methods from the various disciplines, the main ones being a ballistic coefficient screen, highlighted by the blue line, a minimum lift during landing, highlighted by the black line, and a return payload, and whether the vehicle had the capability to carry the return payload volume internally, which is the dashed black line. With the solution space screen, we then had to verify our results. We plotted the Dream Chaser reference values that we had next to the portion of the solution space that passed screening. And then from there, we were able to identify and select a design point. We prioritized the maximum payload weight first, then secondary emphasis was given to the minimum takeoff gross weight. A third consideration, since this is a reverse engineering project, was to cross-reference the design point with the Dream Chaser's reference values. As you can see on this table here, we assembled all of the various geometric and weight parameters for the design point and a Dream Chaser estimate, and we determined that most of our design point parameters matched very closely. With a sized vehicle, we can now move into the configuration layout phase to figure out what this vehicle looks like. The main objectives for this phase are to determine the outer mold line, create an internal configuration layout, and create a higher fidelity mission definition. Geometry and systems will take point on the process to create the outer mold line and create an internal configuration layout, while the trajectory and performance discipline will take point on creating the higher fidelity mission definition. The other disciplines will serve primarily to provide inputs as required by those two disciplines, and synthesis will join in as a glue role to help make sure everyone is communicating properly. Since this is still a very multidisciplinary process, a simplified flow diagram has been made to show the basic relationship between our inputs through the various disciplines through this process to achieve our final output results.
For geometry systems, our goal for scale is to lead the team in creating a parametric outer mold line with a configuration layout. We start off by taking inputs from synthesis, TMP, WBSM, literature, and propulsion. And then we utilize methods from Roxman's aircraft designs, parts 3 and 4, and then Nikolai's fundamentals of aircraft design, along with CAD modeling. From this, we're able to derive an initial outer mold line and configuration layout sizing for certain parts like landing gear and avionics and systems like that. With that, we also prepared it with our PS design point and the HL20 and space shuttle geometry.
Overall, as you can see, we were able to produce a CAD model based on our design point parameters with relatively low error between them. This includes important parameters such as tau and planform, and this model was then handed out to the rest of the team for further analysis and refinement. Very importantly, this is used in our WBSM discipline to identify CG location, as well as estimated moments of inertias and TPS layout. For this, we worked with the TMP and geometry teams to refine locations for our allotted volumes for our systems, and use statistical curve fits and heat map imaging for our systems.
We developed a component moment buildup method to calculate the location of the center of gravity. Then we worked closely with geometry to iterate the internal layout of the vehicle, resulting in a final CG location of 55.58% of the body length. We also estimated the moments of inertia using a statistical curve fit generated from historical lifting body vehicles.
For our TPS, we used a thermal imaging of the space shuttle and identified 3 major areas, critical areas for our vehicle, and that being the nose, the leading edges, and bottom face, since those receive the highest heating loads. We also noticed that they put their most protective materials in those locations, and we'll be using a similar approach in our model seen over here, by placing 2 front along the leading edges and nose, and then 8, 12, and 8 along the bottom and the top surface.
For the structure of this, we took a look at the loading conditions of it, and then we based that off of our rib density needs to be along the nose and aft area, while we have a longitudinal keel beam density. We verified this assumption using a preliminary study of the manned version of the Dream Chaser, which is shown with this image that hyperbolates the bending moments of the structure. And then from this, we were able to define an initial layout to be given to geometry for their configuration.
The first goal of stability control is to determine the initial size and configuration of the tip fins, center fins, ailerons, and body flaps. First, we use the outer mold line just defined by geometry and the refined center of gravity estimate from weights, along with a modified version of the HL20 tail volume coefficient to determine the initial vertical and horizontal tail sizes. As you can see in the next slide, we're able to use these areas to determine the planform area and geometry of the tip fins and center fins and the control surfaces, which is then verified by comparing it directly with the published data from the Dream Chaser itself. These geometries are then passed on to the geometries, weights, and aerodynamics disciplines to further refine the vehicle outer mold line, weight and inertia characteristics, and aerodynamic characteristics.
All right, for RCS layout and sizing, during the seal phase, the main goals or the main objectives were to determine the inertial thrust layout, compute the required control moment, and evaluate RCS control authority. And the main inputs that we used were the CD location for geometry, thrust force for propulsion, the docking constraints for the IDSS. And the methodology that we used is the thrust, the rigid body dynamics to compute the required control moment. Then we used the thruster moment equation to relate the thrust force and the moment arms to the control moment. And on the next slide, the verification table, as you can see on the required forces on the far right-hand side, they are much smaller than the available thrust, which proves that the RCS does have enough control authority, and the initial thruster layout can be carried forward to the following phase of the process.
In addition to sizing and control effectors, stability control defines the design constraining flight conditions, which serves as the backbone for risk assessment and refined sizing later in CE. These constraints come from literature, regulation guidance.
For the propulsion discipline, the main objectives of the CL phase are to determine parameters for the engine propellants, size new engines, and provide a propellant tank volume. To do this, inputs from synthesis, WBSM, TMP, and methodology from Humboldt was used.
By keeping our maximum thrust constant from the parametric sizing phase and using that sizing methodology provided by Humboldt, we were able to size our own RCS system, and we yielded a higher engine thrust to weight ratio of 13.73. We then delivered this maximum thrust to stability and control, the total propellant volume to geometry, and the tank pressure to WBSM for further analysis.
For the aerodynamics discipline, the main objective for the CL phase is to determine parameters that constrain the outer mold line. To do this, inputs from WBSM, TMP, geometry, stability and control, aerodynamics, and literature review are used. To determine geometric thermal constraints, methodology from Henke and the radiation equilibrium temperature method were used, and to determine the airfoil selection and planform area, a winglet thermal feasibility study and parametric planform generation occurred. The main thermal outputs for the CL phase are winglet thermal feasibility and a nose temperature investigation, using a maximum allowable temperature provided by WBSM. These outputs are used for the geometry and stability and control disciplines and are verified using similar reentry vehicles. To determine the planform area, the main factor was the half-chord angle. To determine the half-chord angle, a geometric investigation was done on the HL20 and similar lifting bodies.
To finalize our model for geometry, we took the finalized inputs from stability, aerothermal, weights, TMP, propulsion. With this, we were able to finalize outer mold line shape along with a full configuration layout of our internals and landing gear, fin placement, and fin size. We then re-verified this with our PS design point, HL20 geometry, and space shuttle geometry, and from this, we were able to finalize our model to be used in CE.
Finally, to close out configuration layout, trajectory performance was tasked with two main responsibilities, which was collection of parameters for risk assessment in CE, and the refinement of our mission profile introduced in PI. To do this, an extensive literature research was conducted, and from that literature research, we found restraining parameters such as the landing sink rate used by weights and geometry, and we also found medium fidelity analysis methodologies for ascent, reentry, and orbit. This included 3 degree of freedom flight for our spherical non-rotating Earth for ascent and reentry, and then a co-elliptic transfer beginning at 250 kilometers for our orbital model. Our ascent model is used for verification that we can reach our insertion altitude and to provide initial orbit conditions. The orbit model is used to provide a refined weight ratio estimate, and our reentry is mainly used to evaluate these parameters for our risk assessment. And on this next slide, you can see our refined mission profile that now includes these mission times gathered from literature and the co-elliptic transfer.
Now that we have a vehicle outer mold line, a internal layout, and a official trajectory, we now have an official vehicle, which we have dubbed very on brand, the Flying Squirrel. We then pass this vehicle, the Flying Squirrel, into the configuration and evaluation phase, where we can begin to perform the various risk analyses and make a final vehicle selection. The main objectives for the configuration evaluation phase are to identify and run analysis, technical analyses at all various design constraining flight conditions, other technical risk assessments that occur under other conditions, perform a non-technical cost assessment of the vehicle for profitability and market competitiveness, and then at the end of it, make a baseline vehicle selection to push forward into the preliminary design phase. Synthesis will take more of a managerial role in this phase, coordinating the disciplines to better perform their interdisciplinary, to identify and perform interdisciplinary risk analyses, as well as properly allocate resources. The cost and marketing discipline will primarily head the non-technical cost and market assessment, while the other disciplines will perform their individual disciplinary analyses with guidance from synthesis. As this is, again, an interdisciplinary process, we've created a flow diagram to show how we went from our inputs through the various disciplines, how they connect to achieve our main outputs for the phase, which will lead into a final baseline vehicle selection.
Vehicle risk assessment begins with stability control by evaluating the effectiveness of the flight control system at the design training flight conditions that were identified in configuration layout. The goal here is to ensure that the flight control system has enough control authority and is able to maintain static trim conditions throughout the entire flight regime, particularly in the most critical phases of the flight. This is done, to do this, we begin by taking aerodynamic moment coefficient inputs from aerodynamics and inputting those into Altair flight stream and digital DATCOM to determine the static stability derivatives of the vehicle. Next, we input the weight data and geometry data with the static stability derivatives into the 6-degree freedom equations of motion to evaluate the control forces and control deflections required to trim the vehicle in flight. Once this is completed, we're able to determine the final configuration size of all the flight control systems and also compare the static stability derivatives to the published regulation requirements to determine, to ensure they remain within limits. At the conclusion of this process, which is still ongoing, the vehicle will have a fully configured, fully sized, and safe flight control system.
The goal for the aerodynamics and thermal discipline during the configuration evaluation stage is to verify that the OML generated in CL can produce the required lift and drag coefficients across the entire flight profile, as well as survive the very harsh environment of reentry. We do this through inputs from geometry, TNP, and WBSM, as well as literature review to compare against other vehicles, and also various computational program manuals to make sure that we are doing it correctly. It's very important. Our methodology includes using a combined approach of low fidelity CFD for subsonic, and then using a boundary panel methods using CV Aero and Altair Flight Stream for the supersonic to hypersonic regimes. Next slide. Okay, and then here you can see a validation between our moment coefficient untrimmed at Mach 6 against the HL20. We followed closely, very similar in magnitude and shape. This is being optimized to stability and control. Here we have our L over D max across the entire Mach regime we're going to be seeing, again, showing about a 4.8% error against HL20. These are being delivered to synthesis, trajectory and performance, and stability and control. Next, more validation needs to be done with this to determine the actual effect, to determine the, to compare the effects of the changes made through this. But through verification of checking with WBSM about the maximum allowable temperature, 1900 Kelvin, we can see that the original OML of the vehicle developed in CL on the right-hand side was well above the heating limitations of the material for TIFR. And this was then handed over to geometry with the concerns made, and then the vehicle on the left-hand side shows that the vehicle is now thermally more survivable during reentry.
The risk assessment performed by Trajectory and Performance utilized those models introduced in CL, combined with the PS Air model. We then evaluated these models with parameters identified in literature, and on the next slide, our model passes on all criteria except for our landing sea speed, And this is mainly attributed to how our re-entry trajectory was developed. And this is then delivered to synthesis for consideration in our final vehicle configuration.
The objective for the WBSM team in this stage was to determine minimum thickness requirements for our TPS. And these critical heating locations being, again, the nose, leading edges, and bottom base. In order to do this, we worked closely with the aerothermal team and geometry teams to modify the geometry as much as possible. And we used an equivalent heat pulse analysis as well as a steady state analysis to achieve this. We verified our method against ArcJet heating test results as well as the two-part pattern. And we determined that at our effective nose radius, we determined we need a minimum of 3.1 inches to survive. And in the next slide, we can see our thickness distribution of our TPS as we go along the chord to the rear. As you can see, there's a decreasing thickness as we reach the rear of the vehicle.
Okay, for cost of market, a question I'm sure all the investors might have is how much does it cost to build a dream structure? In order to give you an answer, we had to look at several cost models, and we came across the trans-cost model by Squirrel, and we decided to use it because it focuses on space launch systems, and it's available to us. It's a TIM. And next, it also uses the cost CRs, cost estimation relationships, with inputs from weights, propulsion, and trajectory performance. And the outputs we'd be able to showcase are the flight cost per flight to the vehicle, the specific transportation cost, and finally the life cycle cost, which will determine the profitability of the vehicle.
With our model selected and inputs given, we are able to first output our first two outputs of cost per flight and specific transportation costs, or dollar per kilogram, to the ISS. This is calculated with a launch cadence of 6 launches per year. And as you can see, it's in the table on the top right and split into the recurring launch costs of the Vulcan, the recurring operations cost, and then the total cost, which consists of those recurring operations costs and the amortization of both the production and development of our vehicle. We then needed to verify our model, so we found the cost per flight of 2 other vehicles that delivered payload to the ISS, and then compared it with our model's output. And as you can see, there's a low % error, so we felt this model was verified. We then wanted to compare our vehicles dollar per kilogram to the ISS, and as you can see, it is quite a bit more expensive than the other vehicles, meaning it's already off to a bad start in the marketplace. And then lastly, we wanted to do the life cycle cost of our vehicle to determine if it's profitability. So we chose a 10-year life program for the vehicle, and then we plotted the profitability based on the launches per year. And as you can see, our profitability is quite negative, and with a nominal launch of 6 launches per year, we find the vehicle not viable, and it would actually take 51 launches per year for our vehicle to reach profitability.
So you notice we went a little out of order compared to other teams, and that's mostly because, well, the configuration evaluation phase is not yet complete. Most of the disciplines are done with their individual analyses, but synthesis is still working on the process of meshing them all together to create a final risk analysis for the vehicle. Most of the risk analyses so far look like they are going to be passing, with key ones that are not passing being the landing, which is attributed more to the model than necessarily the vehicle itself, and then cost, which, while not a technical discipline, is a major consideration, and we are failing quite badly there. That brings us to where we are with the configuration evaluation phase, which now we can go into our conclusion, where we are, where we want to be. As stated before, we have an outer mold line, an internal layout, and a majority of the individual risk analyses are complete. We're still meshing them together. Synthesis is working towards creating a better risk analysis model, specifically utilizing the NASA 5x5 method. But that is still in progress. As some disciplines have yet to completely finish their risk analyses. The goal is to have a baseline vehicle selected and all risk analyses complete to ensure the vehicle passes all mission criteria by the final due date of the project, which is going to be May 7th. With that, thank you.